So in this one, we're going to be looking to compute the volume inside x squared plus y squared plus z squared equals 2. And I recognize that as a sphere of radius root 2. So this is radius equal to root 2 sphere. And then outside x squared plus y squared equals 1. And so this is a cylinder best described as r equals 1. So now it's a question of, okay, so which option do we choose? Do we use spherical or cylindrical? So let's try setting it up in spherical first. So to get an idea for this object, let's take the sphere of radius root 2 as seen from the side, like this. And let's see, so here's some axis. Just drawing this end on for simplicity, no 3D. And let's see, so looks like we've got out here 1, and then we've got at root 2. And so here's our r equals 1. And here's our rho equals root 2. Okay, so let's see then. So the region that we're interested in, it's outside the cylinder. So that means for a line coming out here, it's going to be inside the region over here. Actually, let me change to a different color. So the region that we're talking about is going to be this part right here. So let's see, where does this live? So from the point of view of spherical coordinates, I'm going to start with phi equals 0, come down here to phi equals pi over 4. And then I'm going to be going all the way down here. So this is phi equals 3 pi over 4. Okay, so we've got 0 to 2 pi for our theta, and we've got pi over 4 to 3 pi over 4 for our phi. And now we need to figure out the radius rho. And so for this one, let's see, the starting point here is given by this line, x equals 1, or if I said, I mean, I can talk a bit about, I can talk about it as x equals 1, in which case it would become rho sine phi cosine theta equals 1, and then that would be a mess if I try and solve it for rho. So instead, I'm going to say, no, let's not do that. Let's consider it as r equals 1. And in this case, it's rho sine phi equals 1. And then I get the much simpler rho equals cosecant phi for my starting point. So I'll go with that one. And then the outer bound is just going to be root 2, as we saw before. Okay, and so then I need my, so this is volume, so we're just integrating 1 times the Jacobian. And there we've got our spherical setup. Now, suppose I'm looking at this and thinking about, okay, I'm going to have to integrate this thing. This rho squared is going to become a rho cubed, and I'm going to substitute this into it, and I'm going to have to integrate a cosecant cubed, and that does not sound appealing. So maybe this is not the best way to set this one up. All right, let's do a do-over. And so this time, let's see, so I'm going to do it now in terms of cylindrical. And so I'll still have my 0 to 2 pi for my theta. And then let's see, so supposing I want to do the dz as my innermost integral. So I'm going to set this up r dz dr d theta, like that. So if I'm going to do r, let's see, here I'm going to draw myself a little doodle of it again. Basic idea here is that we're going to be doing cylindrical shells, right? So we're going to be integrating dz through these slices, and so I'm going to be picking those slices up from r equals 1 to my last slice, which is just a point at r equals root 2. So this is 1 to root 2, and then z is going to be going from top to bottom here on any one of these. So it's going to be going from the bottom curve up to the top curve here. So let's see. So that means I need to go back to my sphere. So this, these points here are coming from the sphere equation. So I go back to my sphere equation and say, okay, so this becomes r squared plus z squared equals 2. So then that tells me that I've got z squared equals 2 minus r squared, or z equals square root 2 minus r. So I'm going to be going from minus root 2 minus r squared up to positive root 2 minus r squared. Okay, and that one I think I can actually integrate. So let's see. So for the first step, I'm going to simplify things and change this to 2 times the integral from 0 to 2 pi 1 to root 2 0 to 2 minus r squared. So we're just looking at volume. So I'm just going to find the top volume, the volume of the top half, and then double it. Okay, and so then let's see. So we've got 2 times 2 pi times, and then we've got our so that one's got an r in the bound, so we can't Fubinate it any more than that. So let's see. So now I'm just integrating z, and when you're integrating something from a to b dz that looks like this, you're just going to get b minus a, right? So in this case, b minus a looks like root 2 minus r squared minus 0. And that's sort of nice because I've got something here that looks like a good setup for a u substitution, 2 minus r squared for my u, and then my du will be minus 2r dr. And so if I pull the minus 1/2 over to the other side, then I have that right here. Okay, so this becomes now, let's see, so one of those 2's is going to cancel, minus 2 pi, and then I have the integral of u to the 1/2, and yep, that's looking good. Okay, so minus 2 pi, and then I've got u to the 3/2 times 2/3, and u here is going to be this 2 minus r squared. And where do I put my 2/3? So bring my 2/3 out. I have just stick it out there for now. And so we have minus 4 pi over 3 times, and then substituting in, I'm going to get 0 minus 1. So I end up with 4/3 pi. Nice.